brother, and we won't take any questions on that during the talk, but afterwards you may wish to talk to him. So Erik got his PhD at Utrecht, and from there he went to the Institute for Advanced Study, and then to CERN, and then back to professor at Utrecht, and then to Princeton University. Around here we know it as the College of New Jersey. And now he is a professor at the University of Amsterdam. In addition to all of these talents, he plays chess, he plays the piano, and he's a composer. And he's going to tell us today about a new way of thinking about gravity. And I think sometimes you use the term entropic gravity, is that right? And what I really liked was a quote, and I don't know if it's from you or someone describing your theoretical ideas, is that instead of thinking about particles and forces, we should think of everything being made of information. So, Erik, please tell us about emergent gravity from dark, I forget what the title is, it's right up here, from emergent gravity to dark energy and dark matter.
Thank you very much for this introduction. I'm pleased to be here and to tell you a bit about recent work that I've been doing, but also about recent developments on thinking differently about gravity. Indeed, it seems like we are changing the language in which we are thinking about space-time and gravity from by thinking about it more microscopically and thinking about it as a emergent phenomenon. So in the talk I'm going to describe a way in which this may shed light on dark energy and dark matter and maybe explain things in a different way than our usual paradigm. So clearly general relativity works very well, and we have been testing it in spectacular fashion, especially, well, already starting in our own solar system, but then further out we have pulsars, and most recently the gravity wave detection, of course, is a spectacular confirmation of Einstein's general relativity, and in particular the Einstein equation. And so we have a lot of confidence that this describes all these phenomena very well. Then, assuming that general relativity works, we go to other phenomena that we understand perhaps a little less, namely these kind of things, where we see that the amount of matter that we observe is not sufficient to explain the bending of light here or what happens in the bullet cluster. And this is where we see the evidence for dark matter. But if you really take it seriously, we see this evidence by assuming that general relativity also works well in these circumstances. And why wouldn't it? So I'm going to focus on some of these phenomena, and in particular the rotation curves in my talk, because I really want to suggest there might be another way to think about it. But why do we need that? I think that, just to summarize what I just said, actually, that general relativity works well, and actually is conceptually also very elegant, and it's convincing as a theory because it's based also on principles, the equivalence principle, general coordinate invariance, and it's very hard to modify this in some way that, well, leaves all these things intact. And indeed, there's no reason why it would work differently in these circumstances at large distances or at low acceleration. So then we come to the dark matter, and we call it a hypothesis, in the sense that you have to assume that something exists, and then you can explain a lot of things, and you can indeed have a lot of successes in explaining the data that are being observed. But the belief in dark matter actually comes from the belief in general relativity. So if you think this is the theory of gravity in all circumstances, then we have to conclude there's this additional part of the universe, what we call dark matter. And of course, this is part of what the successes are about, is that we have different observations that all combine to the standard cosmological model, where we have a certain amount of matter that we can only account for when there's well, dark matter as well in this. So these are all observations that have been explained in the current cosmological model, and any theory that wants to go beyond this has to sort of do equally well. Well, it cannot do so instantaneously, but first of all, I want to emphasize that what you need is also a new conceptual idea. And I want to explain this in the next what are the new ideas? I want to focus on something called entropy, you already mentioned. We know, of course, the energy content of the universe, but if you ask what is the entropy content of the universe, then within the current laws that we are using, if we just use standard model physics, most of the entropy is contained in this little bit, which are the photons. That's about 10 to the 90. If you would associate entropy to the black holes, some people would say that would be 10 to the 100, but this is not an entropy that we understand from standard model physics. So most of the energy of our universe doesn't seem to be associated with any entropy. I'm claiming that is a mistake because I'm going to actually argue that most of the entropy is actually carried by the dark energy. And that will change a lot the dynamics because the entropy is going to be much larger than these numbers. There's an entropy in our universe. If we think about our universe as having indeed a cosmological horizon, so I'm going to actually make an assumption here. So I'm not going to write down equations that are going to describe the entire evolution of the universe from the early stages on. I'm going to actually think about a universe as being dominated by dark energy. And if I have a universe only with dark energy, I have a cosmological horizon whose size is given, if you take the current Hubble constant, has an entropy associated around this number, so much larger than any entropy in the universe. And that entropy must somehow be associated with the dark energy. That's going to be my main argument that I'm going to use actually to say things about what's going on in the universe and even in galaxies. So I'm going to need to argue that what's happening in galaxies has to do with information or entropy carried by the dark energy, and that's going to be sort of surrounding it. And this is going to be a picture I'm going to relate to observations later on in my talk. So where does this link with information come from? Now maybe I should first show you this one. Because I always get this question later, well, what about the bullet cluster? So I'm going to actually immediately start with that one. So if we're going to think about gravity in a different way, how can you explain this if there would not be any dark matter sitting here? Because we see, of course, clearly a separation between the ordinary matter and this. So for this I'm going to do a little bit of an experiment, but first let me think about the following question. We have been using laws of physics, or deriving laws of physics, by observing the universe and writing down our laws in such a way that we can describe what's going on. But if you look at the history of the universe, if we take that to be sort of 1 year, the humans arrived 1 minute before midnight on the 31st of December. And if you ask how much time did we use to do observations, about a fraction of a second. So can we figure out all the laws of physics in that amount of time to describe the entire history? So I'll do an experiment with something that we could have sort of seen as a model for our universe. It's a ball that I'm going to bounce, and it's bouncing, and it has a theory that we can describe. So the bounce is what is our time in the universe, and we can observe it, and we can describe it using elasticity, and we know exactly what it does, and we have a theory, and I call that a theory of general relativity that describes what's going on. I'm going to put this ball here, and what you'll find is that I'm going to wait, and it's going to deform and flow very slowly in a way that I have no way of figuring out using the theory of the bounce. Because if I use a really bouncing ball and I put it there, it will stay in its shape. But there's something now very slowly happening that I have no way of knowing when I would only view the bounce. So the theory that is the response of space-time, the short time scale response is like general relativity, where we can indeed describe things very well, but if we look very long, things might be different. So the large entropy that I talked about can be difficult to see, because if you have a state, even in materials it's very well known, if you have a state with zero entropy, which is quartz, it behaves very similarly as the glass. But this state has lots of entropy in it, and this one doesn't. And this large entropy density may be difficult to detect because the high energy is very close to the ground state. And furthermore, it's a system that's out of equilibrium. So we're going to have a very slow dynamics, and this is called quasi-dynamics in the condensed matter literature. because it is something like what glass does in a time scale of centuries. It flows. So if space-time has a very similar property, actually it leads to certain things are called memory effects if it's out of equilibrium. I'm claiming that dark energy actually is turning space-time into a glassy system which has a slow dynamics and memory effects. So the system that I have here indeed shows this as well, and this slow dynamics is taking place in this polymer because you have to understand really what it's made of. By going inside the material, you can understand its properties. So this is the silicate, that's the thing I just showed you, which you can bounce, you can deform it, it can flow, this is actually what's happening now on the table, but you can even shatter it, and it has different behavior on what time scale you look at. And space-time may have the same thing. So if there is a cosmological time scale where space-time is doing this, if you would describe it by the theory that describes that, you would conclude there's an enormous force acting on this by the wrong theory. I'm claiming this is what's going on in the theory of space-time, and I'll come back to this example actually, and let me mention, by the way, that this is not an easy system to describe. If you describe it, actually you earn a Nobel Prize for it. So this is Dejean, who actually got the Nobel Prize for describing silicate and different. And actually, if you look at the, actually this is from the Academy, and actually I covered it up anyway. There is a picture, would be a picture of silicate here. He made a model of polymers that are doing all kinds of things where they replicate in little tubes. I'll come back to this later because I'm going to use a calculation from this physics to compare to what the properties of space-time are. But the main point I want to make is that there are different laws depending on different time scales, and this is a conceptual point about also the properties of space-time. We may not have probed space-time yet at these long time scales to be able to see this. So, as I said, I'm going to actually make an assumption to think about a universe only with dark energy, and then we are living in what's called superspace, and we have a universe which has a horizon, and actually going to view it not in the usual exponential growth picture. If I have only dark energy, you can write down a static metric where we can put ourselves in the origin, and we have a horizon sitting at this radius, which is the Hubble radius. And this horizon has very similar properties to horizons of black holes, in the sense that you can associate an entropy to it. And this is how I got to my number of 10 to the 120. So let me take now a little bit of a step to another topic, namely black holes. So here we have indeed laws of Bekenstein and Hawking that tell us what are the entropy and temperature of a black hole. There are these famous equations that are the area measured in Planckian units, and the temperature is related to what's called the surface gravity on the horizon. And then you can derive from Einstein's equations the following law. So if you change, namely, the mass by throwing a little bit in, the area of the horizon changes. And this is an equation you can derive from the Einstein equations. But it looks very similar to this one. Actually, it's identical to this if we make these substitutions. And this is an equation we know how to derive from statistical mechanics. Namely, the first law of thermodynamics, which if you have a microscopic explanation of this entropy, then we can derive this. We don't need to assume it. We don't have to write it down as some fundamental law. No, we can derive this from statistical mechanics. So if I have a microscopic explanation of this entropy and of this temperature, I can derive this equation. And then I derive the Einstein's equations. So that is the idea of emergent gravity. It's basically to go to a microscopic theory that explains this entropy, then do what we normally do with statistical physics and thermodynamics and derive the Einstein's equations. One important thing you have to then explain or even assume is that this entropy is going like an area. Because if I take this equation, I can get back this equation. But if I write some other entropy here, I will not get back the Einstein's equation. So I'm going to actually argue that the Einstein's equations are correct, but indeed that this entropy has some interpretation microscopically in terms of some entanglement. And that's again a connection with the information or the quantum side of the space-time. So we're going to have to think about space-time in a much more microscopic way to explain these expressions. Because you notice h bar is in here, but if I multiply the two, the h bar actually drops out, so there's no h bar in this equation, but it is in the microscopic interpretation of these boxes. So understanding this entropy is actually analogous to trying to understand the microscopics of this material, because we can also maybe understand whether there's a dynamics or a temperature associated with it. And that is indeed what is expressed here. So this is a thought experiment that you can do near black holes, which was done by Bekenstein. Actually led him already to sort of discover this entropy law of black holes. But he proceeded also to argue that there must be an upper bound on how much entropy you can associate to a regional space which has a certain size r and a certain amount of matter m in it. So m is the energy sort of in this box. And his thought experiment by which he determined this entropy was by as follows. He put the box near the horizon of a black hole. He holds it there with a certain rope which has a force which is determined by the surface gravity. So the force over mass is the surface acceleration or surface gravity. Now if you lower the box, the entropy in this box disappears and goes in the horizon, behind the horizon. And therefore some entropy is being reduced, but the entropy of the black hole is being increased. And you can calculate by how much. Namely, the work that you do is F times R is equal to the temperature times the change in the entropy of the black hole. So delta S is actually the change of the entropy, which must be larger or equal than the entropy in this box. And the reason is that otherwise the entropy would go down. Namely, I've removed the entropy from the box, and the entropy of the black hole has increased by this amount. So this must be the upper bound of the amount of entropy in the box. Now, if you work it out, the nice thing is that the force contains the surface gravity, but also the temperature does. So this kappa actually drops out of the equations, and you get an equation that only involves the mass, the speed of light, the size of the system, and h bar. This is called the Bekenstein entropy. It's the entropy associated to a mass and with a certain size and a radius r. Actually, I'm going to see this equation coming back later in the talk, and this is why I'm emphasizing it here. Actually, I'm going to apply it to galaxies. So, indeed, in a galaxy, we also can think about this as a region of space with a certain amount of mass and a certain size. And I can think about the horizon. Instead of having a black hole horizon, I'm going to take the cosmological horizon. The cosmological horizon also has a temperature, it has also an entropy, and the temperature is incredibly small, namely determined by the Hubble constant. So the dynamics of the system is very slow. It's sort of the typical time scale, Hubble time. This is the entropy, and that is enormously large. This is 10 to the 120. And I claim that this horizon appears because we have a positive dark energy. So I'm going to associate this entropy and the temperature to the dark energy in our universe. And later on, I'll indeed sort of say that this entropy is not just sitting on the horizon, it's actually associated with the dark energy that's filling the universe, because the dark energy is really everywhere present. So this is the way it might actually affect even dynamics more locally in our own neighborhood. Indeed, one calculation I can do, which is very similar to the calculation that Bekenstein did, is namely think about what happens to the size of the horizon when I put in matter. So I first take an empty de Sitter space without any matter in it, but I add matter in, say, the center. Then the horizon actually gets shifted a bit because it's now at a new equation. This is the equation that determines the position of the horizon. There should be 2 here. Oh, no, there should be 2 here. That the location actually, when you solve this equation, gets shifted a little bit, and the horizon gets a little smaller actually. Instead of larger, it gets smaller by an amount which is the energy in the system, mc squared, divided by the temperature. So it's like the first law, and this is the change of the entropy of the horizon. But look at the minus side. But I also wanted you to point out this ratio because I'm going to rewrite some equation in a bit exactly in this form. So this is energy divided by temperature. which indeed is an entropy. I'm going to go to galaxies, because here is an observation of what happens at rotation curves when they start deviating. That happens at a particular acceleration. That acceleration can be written in terms of the present day. I will consider this an observation due to Milgram, that this flattening of rotation curves actually always, no matter what the size of the galaxy, seems to occur when the acceleration drops below this value. I'm going to write this equation in a slightly different way by putting in some 4 pi's and some h bars, which is mc squared over a temperature, and this is an entropy. The A is just a 4 pi r squared. So this equation tells you that when this ratio drops below this number, somehow this starts happening. And that's an observation that seems to be true, and actually I'm going to relate it to the equation that I have here, because you see the same quantities appearing here. Change of the area and the same ratio appears. Before I get there, I have to tell you more about entropic or the entropic or the emergent gravity that we are looking at. So, indeed, I'm going to say that there's some way that this might be the consequence of thinking about gravity in a different way. I'm not going to do this in the Sitter space. I'm going to actually do this where string theories like to work. String theories, for some reason, they like anti-de Sitter space. It's not close to our real world. And the reason is that, of course, in the Sitter space, you have the minus sign. If you put the plus sign here, it's a space with negative curvature and it has a boundary. And string theory likes this more because this is where we can use supersymmetry and we have a much better understanding of what the microscopic theory looks like. There's even a description of what's going on in the bulk, which is inside the space, which is called the bulk, and the boundary has a microscopic theory on it from which we can derive the gravitational laws in the center. That's also an example of emergent gravity, where we start from a microscopic theory without gravity, and the gravity emerges in the bulk. And actually, this is a standard picture you see in popular descriptions. One way that one thing to learn from it actually is how to think about entropy of black holes. Because black holes have a description in the microscopic theory in terms of the holographic theory of the boundary as a thermal state. A thermal state of, in conformal field theory with lots of degrees of freedom and which are exciting. So when you think about individual particles in the bulk, actually they are like particles moving around where most of the degrees of freedom of the boundary theory, or the strings I should say, are in that ground state. In particular, the open strings stretching between them. I call this a Coulomb branch. This is sort of the terminology of string theory. When you throw the particles into a black hole, they become excited. All of these string modes, they thermalize and form something what's called the Higgs branch. So there's many more degrees of freedom that suddenly appear here, and that explains these entropy laws and even the temperature. One effect that actually happens is that the density of states becomes enormously large, but the temperature goes down and there's a much lower set of excitations and energy necessary here than we would have here. So here the theory has individual particle states. Here it's sort of a very dense state with a very high entropy. So this is happening for black holes in this theory. It actually happens more generally in string theory, and actually I'm going to argue that a similar way we can think about the entropy in our universe. So one other thing I want to mention here is that ADS has this conformal boundary on which we can put some microscopic theory which lives on this boundary. So this is the same picture, is some part of the boundary here, where if we go into the bulk, we have actually think about this as a scale direction where we go from the short distance UV scale to the IR, which is almost like the inverse of what happens in space-time, because so the UV here corresponds to the boundary and the IR in the center. And this is indeed a phenomenon in string theory that happens. It's called the UV-IR correspondence. Now, but I already mentioned that the gravity then in the bulk actually emerges from integrating out degrees of freedom from the bulk, from the boundary, which is this microscopic conformal field theory. One thing I want to point out is that ADS space-time itself is the ground state. It really is the lowest energy state of the system, and therefore it actually basically is an empty space. So I already mentioned a bit of entanglement entropy. You may not be too familiar with this, so I'll briefly explain what the idea is. So entanglement is defined when you have a quantum state of a system that you can divide up into two parts, an inside and an outside, and you think about then the Hilbert spaces associated with two regions. You trace over one region, say the inside, or you trace over the outside, and then you're left with what's called a density matrix for the inside Hilbert space, and the entropy then is defined by this formula due to 4 minor. And it can sort of be thought of as measuring the bell pairs that you need to sort of entangle the system inside and outside. So there are particles or states that are correlated quantum mechanically that are being counted. It's an entropy very much like any other entropy in the sense that it also has a first law, and that is the one that's going to appear in a minute. So Mike already mentioned that I think that everything is made out of quantum information, even matter. This actually goes back to John Wheeler. Who called it from bit. Nowadays we call it from qubit because we make it quantum information. And there are ways of deriving indeed the Einstein's equations in this setting that I just described in de Sitter space if you take the following, or make the following observation. So here's this boundary, and I have the region which I call now B and A, and there's an entanglement associated to it. And Riemann Tagliani discovered that this entanglement entropy is exactly given by the same equation that Bekenstein and Hawking had, namely the area of some minimal surface that extends into the dot. And that area, that is now interpreted as an entanglement of this state, the microscopic state of the theory. Now, you can actually derive the gravity then by writing down the first law of entanglement entropy, and then general relativity requires this area law to be true. I mean, it holds in any de Sitter space, but this is not the space to live in. So we have to try and extend it to de Sitter space and then see what happens over there. So these are, as again, this is the work by many people, and this is a development that's going on, and actually it has already been described in many papers or popular discussions. The basic slogan is that there are some entanglements that makes space-time. I'm not even try to explain everything what's going in here, but there's some idea that indeed you sort of connect space-time by sewing together different spaces using entanglement. And maybe this is indeed what I can say about this. Actually, the slogan goes by the name EPR is equal to ER, where ER stands for Einstein-Rosen. So this, if you think about this as a black hole, there are two spaces that are being connected, namely spaces are connected by a wormhole. That is the space, if you cut it down here, looks geometrically like that. And this neck around the horizon actually counts the entropy, first of all, but also the entanglement between the two regions. So there is a microscopic vacuum state. So this looks like a vacuum. The vacuum has entanglement in it, and it has entanglement between the two wedges here, left and right. And that amount of entanglement is exactly given by the area of the horizon. And so the idea is that entanglement is responsible for connecting these two regions, because if you reduce the entanglement, actually this area goes down and sort of you cut these two spaces apart. So we're making space-time, we're really looking microscopically at what space-time is made of. This is the Sitter space, also a Penrose diagram, and microscopically you can also write down a vacuum state very similar. However, now we have two parts of the space, the inside and the outside of the cosmological horizon, because the cosmological horizon is here and that's in the middle. And you can also think about this entanglement between the two things. So this is empty de Sitter space, but so you may ask what's being entangled on the left and the right. I claim it's associated with the dark energy. And that dark energy carries an entropy precisely given by this area. Yeah, actually, I think I already mentioned this. I mentioned the first law. I may not go into details here. I mean, this is sort of details of how to explain how general relativity can be derived from quantum entanglement. I mentioned that entanglement entropy has a first law. Turns out that first law can be actually written in this form, and this can be shown to be equivalent to the Einstein's equations. Namely, if I can do this for every region that sort of looks like this in space-time, this is called, by the way, a causal diamond. You can think about this as part of the zero space even. This was pointed out by Jacobson. And if I can derive this equation microscopically for every point in space, I can derive the Einstein's equations from entanglement. So this is a microscopic way of deriving general relativity from entanglement. So I want to actually now go back to the ideas about dark matter. I'm actually going to explain a result that's sort of very similar to what I wrote down on the previous slide. Namely, if I put in matter, so here actually, maybe I should show that. I look at the area of this region. So it's again, say, some region which is an inside and an outside. And I ask what happens to the area when I put in matter. This equation expresses this because the matter, of course, has stress energy in it. So there's some left-hand side, which, by the way, if you calculate this, is sort of like the mass times the radius of the system. And the entropy gets reduced. So this is also saying that the area gets reduced, and indeed that's one way to think about curvature of space. If you think about putting matter in here, one way to think about how space is curved is by saying the following. Suppose I fix the volume, which is sort of what we did even on the previous slide. This equation has sub v in here. That means that I fix the volume here, but I change the amount of matter inside, and the area gets reduced given the amount of volume. The same you can do actually in this picture. That's sort of what I'm doing here. I'm looking at the mass and ask, put matter in here. Space is being curved. What happens to the area at a certain distance? It gets reduced, and it gets reduced exactly by that number that I had before. The delta A equals to minus 2 pi m ncr over h bar, which is the expression that Bekenstein had. So the change in the area of a sphere when you have curvature is, I'm going to interpret this actually as a change of this entanglement entropy, is given by this Bekenstein factor. That's an equation you can derive from general relativity, and actually it's something that I'm now going to use to connect to, again, the picture. So I'm going to get back to dark matter, and I'm going to now think about not the entire entropy of this region. So this is the entire cosmological horizon where all the entropy is equal to this area law. I'm going to ask how much entropy is sitting in a smaller region of space. I've told you I have a hypothesis, namely that the entropy is carried by the dark energy and actually is proportional to the volume. So I'm going to write down an expression that tells me how much entropy is associated to a part of the space. So instead of taking r equals to L, I'm going to go to a radius smaller than L, much smaller, say galaxy size. So I'm writing down an expression that goes like the volume. Actually, the volume goes like the area times the radius. So this is a volume law, but it has been fixed in such a way that if I put r equals to L, it reduces to this equation. And it's the only way that equation that does this. So this is exactly just a special case. This is a special case of this equation when I put r equals to L. But this is the volume expression. So now I have two equations. This equation for the amount of entropy associated to matter inside the region with size r. And this is the amount of entropy that's associated to the mass of the dark energy, I say, actually in a region of space of this size. If I now go back to my same equation, I can actually write it like this. So this was the entropy I claim of dark energy inside a certain region. So I take a certain part of a galaxy of a size r, ask how much entropy would dark energy have inside it. That's this formula. The L is determined by the Hubble constant. This is the entropy associated to matter of the same size. If this is smaller than that, that's when rotation curves start flowing. And this for me is a conceptual thing I can understand. Namely, this is the amount of entropy that matter is going to remove from this part of the space. This is the amount of entropy that's present. When this drops below, we start seeing deviation. And I'm actually going to say this here again. So matter entangles with the dark energy, but if this equation is obeyed, it's the same as that equation. This is the entanglement that entropy sort of removes, and this is the entanglement that dark energy has. So we have some way of understanding that the matter actually makes a region of space like the vacuum, because it takes all the entropy out of the dark energy. This is where Newton's law holds. Here, things start deviating when this drops below. And this is going to be made more precise and more quantitative, because now I've only made a qualitative statement about an inequality, but I want to actually say more about what's going on exactly in that region. So I'm going to make some assumptions. First of all, I've sort of argued that gravity emerges from this entanglement entropy, and that we have this area law that gives us indeed the general relativity. In the center space, actually, we have positive temperature and entropy, and actually, I think that tells us that we are in an excited state, and I already told you it's like a glassy state, which has a certain slow dynamics associated to it. I'm going to argue indeed that the same principles that apply here also apply here, but we have to take into account this difference, namely that we have now an entropy density with its slow dynamics. And I'm going to calculate indeed what are the effects that are going on. By the way, I should need to mention this result can be understood also microscopically. I wrote a paper that appeared the day before yesterday, which I just briefly want to mention. I have no time to discuss this in this seminar, but indeed it shows this equation. We derive this from a microscopic picture of holography in non-linear space-time, in particular also the Sitter space. This is an equation that appears in there where we have indeed a way of understanding the entropy content of a region of the Sitter space by basically using some relationship with the Sitter, anti-de Sitter holography. So we have some microscopic understanding of this volume law that I mentioned. So this is one more recent development where I think more about the microscopic picture. And I also mentioned these two phases of string theory, which I briefly want to mention again, because I'm claiming this entropy in the dark energy is related to this other phase of string theory, where there are things that are called long strings. So I mentioned in the title here, by the way, there's a long string phenomenon. That long string phenomenon actually takes place also in the dark energy sector. And the long really means long, cosmologically long. It's basically like the polymers in this system. So now it looks sort of like that by some slow dynamics. And this also will have a slow dynamics of its own that we have not taken into account. Our worldview consists of particles in empty space, not about, we don't take into account the dynamics of this part of the theory, which is indeed, I would associate it with the dark energy. So Newton's law is derived by some entanglement, and it is true at short distance scales. However, when we start going to larger distances, the area law starts losing from the volume law, and the volume law takes over, and that changes the nature of gravity. And I claim it's analogous to elasticity. I want to make that more quantitative by connecting this to some observational effects. These observational facts are, well, basically known as Milgram's miracle, or whatever, observation of law. But it's the following fact. It's actually been put together recently by combining, I think, about 170 galaxies into a plot by Stacy McCock and his collaborators. There's some follow-up work by Navarro Frank, which I may mention later if you have questions. But it basically makes a relationship which connects the observed acceleration, which is the one due to the matter and the dark matter. If you think that there's dark matter, this can be an effective way of describing it. So I'm saying this is the observations, and this is what you expect from baryonic physics. And it shows a very tight correlation. Well, very tight, that's also by some clever way of plotting it. There's some scatter around it, but there is a relationship that if you follow it, if there would be no dark matter, we would be on this line. So the dark matter is responsible for the deviation. But the line here for low acceleration actually has an empirical law, which is known as the Tully-Fisher relation, which tells you that the square of the observed acceleration goes like the baryonic mass, or say the baryonic acceleration. And here there is, this is an acceleration parameter related to the Hubble constant. It's Milgram's acceleration parameter, but
I am actually going to explain this quantitatively actually from the ideas that I just outlined to you. And including this number, by the way. And maybe I should already point that out. There's a 6 here, which is sort of why the acceleration is smaller than c times h naught. That 6 is related to the d minus 3 here. So this, we did this in any dimension, so there's a 4 dimensions, 4 space-time dimensions, actually this is a 1/3. Actually that comes back in the laws and turns out to be veering up here. I'm going to rewrite this equation in a slightly different way. I'm going to integrate the left-hand side, so this is the acceleration. I'm going to integrate it over the volume, and then the right-hand side also will be integrated. So there's a 1 over r squared here, so I multiply with r squared and integrate. And then I get this equation. So this is the observed acceleration squared. I divide by 8 pi g, and there's again my mvcr. There's the Hubble constant. So this is the same equation if I assume that most of the matter is concentrated in the center, because if I differentiate with respect to r, I get back the same relation. This is an equation I can derive. I'm not going to modify the Einstein equations or the Newton equation by writing down a new force law or writing down a new Lagrangian from which it's derived. I'm going to derive an estimate of an effect, a memory effect that's going to tell me something about the energy contained in the gravitational field. So this is the analog of an expression where you write down an electric field squared divided by 4 pi epsilon naught, 0 or something like that. This is the gravitational analog, so this is the energy contained in the gravitational field. And the right-hand side is also an energy, because this is basically a number and this is a temperature. I'm going to write, get indeed an equation from using an analogy, actually calculating an elastic effect due to the dark energy. So let me actually give you a brief summary of what's happening here. I forgot
Plus
my.
the blank.
I think we dropped the.
Oh, we've got the PowerPoint.
Relation that's going to reproduce this relation by the following idea. I'm going to calculate the effect on a medium when you remove part of its content, part of its volume. So the idea is that the matter it removes part of the entropy of the dark energy, and the dark energy pushes back. And that calculation is going to reproduce this integral equation I had on the board. And that now goes. So now I have. This has been removed due to 2 days, which doesn't listen very well, but I had a caps lock. Yeah, so I want to derive this equation by calculating an elastic effect due to the dark energy. I'm going to describe the dark energy as an elastic medium. So I'm going to remind you a little bit of some elasticity equations that are from textbooks like Lambda or Lipschitz. We have a stress and a strain expressed in terms of the displacement field. These are standard equations for the strain tensor, and then the stress tensor is linear in this. This is like Hooke's law. And the stress tensor is conserved except if there are body forces acting or if there is an interface
or a boundary where there is a normal component to the stress actually defines a traction force on the boundary. This equation is going to appear later on because I'm going to actually think about this boundary as an interface between a region with the dark energy being pushed out and where it's still the other phase of the theory. So it's like a phase boundary between the two phases of space-time, which are called the Coulomb and the Higgs band. But anyway, it's the dark energy say outside and there's an empty region on the inside. One thing I want to mention, just because I'm going to not say a lot about dynamics, but there is also waves in elasticity, and there are two kinds of waves. This is the wave equation. There are shear waves and pressure waves, or P waves, and they have certain velocities depending on these numbers. These are called the Lamé parameters. They're like Young moduli. Actually, for the cosmological dark energy model, actually, I have two particular values. This is the energy density of dark energy. If I assume only the dark energy, this is its elasticity constant, and then you can calculate that the sound waves are actually having a speed which is close to the speed of light, or a fraction of it. There appears to be one particular relationship between these two parameters when you work it out, and this has to do with some property of this medium. Actually, this is one way I actually connect the gravity equations to the elasticity equations. I'm not going to explain the details of it. There is actually a relationship that we can calculate between the displacement and the Newton's potential. This has to do with matching how much entropy is being removed by the matter. I just want to basically show you the final result. Because what I'm going to do is actually calculate the effect, as I said, by removing a certain amount of entropy from the system. Actually, that calculation is very analogous to a calculation that can be done in polymers, the thing that I mentioned before, where you remove some of the polymers from the system. There's a memory effect in those systems that can be expressed in terms of an elastic energy that has proportionality between the amount of volume that you remove, that's this one. So I remove a certain set of polymers, this removes the volume, you get a displacement, and this is the energy. I'm going to do exactly the same calculation. That calculation is basically saying the following: I remove a certain amount of entropy, I already told you how much that is. I can also remove a certain amount of volume that's expressed as follows. If I remove entropy, I'm actually making part of this system empty. The volume is being displaced. I did the same thing at the horizon, by the way. The area is being displaced. And this displacement can be calculated in terms of Newton's constant. If I now do the calculation I just showed you on the previous slide, maybe I should show it here. This is a calculation due to entropy, which is an expression for the strain energy related to the amount of volume that's being removed. I'm not going to go through the details, but this relationship is going to end up the relationship that I want to have by these correspondences between elastic quantities and the Newtonian quantities. In particular, I've already told you displacement is related to Newton's potential. There's also a connection between the strain and the acceleration, which has to do with distraction force, and indeed all kinds of matching. If I take this equation together with these correspondences, I get actually this equation. Actually, I should first write down this equation. But then with that, it comes back to this equation. So that's just a quick way I didn't want to show too much of the details, but there is a way of rederiving this equation from an elastic picture of dark energy, where I know how much entropy is being removed. That entropy is actually given by this expression. And so this is the proportional to the volume that's being removed. And this thing actually comes from matching basically the forces of the elastic medium with the gravitational side. So this is just, again, I don't want to go into the details, but a way of showing you that these ideas can connect to some observational facts. So I've already argued for you that is a reason why the deviation happened at this point, but there's also even a more quantitative way of deriving a scaling law that has been observed. I want to finish with testing it in some other situations. Actually, I'm going to rewrite the same equation slightly differently. This is an equivalent equation where I assume steric symmetry, and then I'm going to re-express it as follows. To be clear, there's no dark matter in this explanation. This is just an effective force that is going to reproduce by representing it as an effective or apparent dark matter distribution. So my equations actually give a prediction about relationships between dark matter and baryonic matter as follows. I'm going to put in here an average dark matter density by saying the dark matter inside a certain region R. I write it as the sphere, the volume of the sphere divided times an average density, also as a function of R. And I do the same with the baryonic matter. I also introduce a critical density, so I expect everything going to be expressed in densities now. But it's going to be the same relation, and that is the same equation, except expressed now in terms of these average densities. So there's one parameter here, which is called the slope parameter of the baryonic mass, which comes actually from the fact that I have to differentiate, when I insert this in here, I have to differentiate the R dependency. So that equation has, can be tested in various situations. It gives already the scaling laws we observed in galaxies. I'm going to compare it to something also in clusters. And I'm also going to do it actually for the entire universe. Because if I think about this as just the average density of baryons in dark matter, this is the critical density. I'm going to assume that these are constants, which means that this is 0. I get a prediction if I put the radius to be the size of this horizon. Because then I get a ratio between these densities. I'm going to show you that later. First of all, this is a test that McGough and others did. Actually, they found a slightly high. This is because the R dependence that I put in, they can adjust the thing that it looks like that. But this has some adjustment of the mass to light ratios that they don't like. But I still actually, with a simple argument that you get this close enough, I find already encouraging. This is a test actually of the same sort of diffusion relation, I should say, due to Marco Brouwer and her collaborators. They have a survey where they use weak lensing. So galaxy-galaxy lensing, so there are galaxies in the foreground. These are background galaxies that are deformed, and they determine the gravitational lensing effect, which gives you the force in regions where there's no traces of ordinary matter, so you can extend the gravitational field much further. Actually, if you look at the distances, it's much further than any galaxy rotation curve would go. Galaxy rotation curves would generally stop here. But this is the empirical relation of Milgram and the one that I reproduced. And actually, it fits the data quite well in the sense that these are 4 different bins with different masses of galaxies, so that the height gets adjusted every time, but it gets adjusted correctly. And here you can even combine it in a plot which is very similar to this radial acceleration relation, namely this one, where here's the baryons, and this is the effect, actually the lensing effect that's being observed, and you get the relation. There's a lot of scatter that has to do with the uncertainties or the measures, the errors in the measure. But the thing I want to point out is that if you look at how far, over how many decades in distance this relationship holds, it seems to be about 3 decades. And that's not so easy to explain using a particle dark matter model. So these lines actually are indeed the NFW profile fits, but there you have a fitting parameter, which is basically the height. The blue line has no fitting parameter. So this is not a fit, this is just one line that can be drawn and not adjusted anymore. The NFW profiles are actually fits. This is a test in a cluster. Actually, this is from data, and it's in a paper from that compares MOND actually, this where MOND doesn't do very well because modified Newtonian dynamics would require this amount of matter, while the amount of matter that is there is only this in terms of the gas. I put in my equations we need this amount of matter. I also put in the stars, and then I can predict something that comes out. Anyway, this is not a comparison to the data. I just looked at this plot and see if I can reproduce this using these equations. Finally, let me go to the plot of what I say was happening here. So actually this equation is the same equation as I had on the slides. It's a relationship between the square of the abundance of dark matter to baryonic matter I took the square root of the relation, but this is the relation, and that's where the data are. So it seems that the same relation also seems to be at least not inconsistent with this, these measurements. So I want to end. I have not described to you anything that dark matter does in the evolution of the universe. I have not talked about the CB yet. This requires dynamical equations. I've just mostly focused on what happens in galaxies, but also the baryonic booster constellations, all the stuff that dark matter does in structure formation is stuff that still needs to be worked out. So for me, there's a lot of things to do, but it doesn't mean that I think there's a discrepancy between whatever is given out of the theory and what's predicted. So let me conclude. This is a summary of what I said, namely that I can argue that gravity is emergent from this quantum information point of view, that if you have an area law that Einstein's equations can be derived, if you take the zeta space, you have to do something new, and there's a possibility of memory effects that would explain these observations. At least I made a calculation that suggests this. And these are things that need to be worked out still because they rely on dynamical equations. I showed you there are dynamical equations that have waves in them. I mean, I don't know whether that's sufficient to describe the acoustic waves that are responsible for these phenomena, but this is still an investigation. And as a final remark, I mean, I think if you take emergent gravity, what does it really make of, well, our current cosmological model? Is it really, can it be consistent in how can we then compare this? I mean, if general relativity correctly describes the short time scale behavior and all equilibrium processes, and that the modifications are only due to the slow dynamics, then maybe if you can show that the slow dynamics behaves qualitatively like cold dark matter, then a lot of the successes that we already have can be taken over without, well, having a different, at least, interpretation of these phenomena, which is not related to any particle interpretation of dark matter or even a matter interpretation. So things could work similarly, but there can be also some differences, which of course I hope eventually there will be, because then you can make new predictions.
Thank you, Erik. We have time for questions. Josh.
So can you comment on dwarf galaxy rotation curves? There's at least one claim that the predictions don't quite match up.
So I've given a simple way of deriving this result. I've not completed a full theory. I've given you a conceptual argument for why something may be happening, and the indication that I can explain an observed scaling relation. That's the main message of my talk. I've not given a complete, so in dwarf galaxies, things work rather well, just as well as most would do. And so I don't think that there's a real big discrepancy there, but it's not like I have fully worked out all details of all the systems. But one thing that I've done here is spherical symmetry. I've assumed spherical symmetric potentials. I think that maybe in those situations we have to be more careful in what the gravitational potentials are. So anyway, there's still work to be done, but I'm not completely discouraged, as I said, about those comparisons.
Emo. Wait for the microphone. Or?
I'm a little confused about one of the final relations you had relating the mega baryon to was it mega dark matter?
Yes.
So mega baryon depends on all kinds of quantities in physics that don't seem to have anything fundamentally to do with gravity, like what's the QCD scale, what fraction of matter formation in the early universe, it depends on all kinds of history as well as things like what's the QCD scale. So, if since most of the energy of baryons is in the energy density of the gluon field, so if I change the QCD scale, I change the baryon, but it doesn't seem to affect anything else that you talked about previously.
So I make a connection between the amount of matter and the effect of this
modification on gravity. So if you would change the amount of baryons, you change the result of this. So this relation is because indeed this comes from an effect of the yeah. So this is an effective description of an effect associated with the baryons. So when you change the amount of baryons, you will change this effect as well. So you're saying that this relation, I mean, in this relation there would be a consequence of your effects you're describing, but not. So this is not just gravity. So how should we say this? I'm feeling I'm not answering your question, but maybe we should discuss.
So you're saying that is that the amount of dark matter you have is tied directly to how much baryon matter there is?
That's what that relation expresses. Because it's an effect due to the presence of baryons have an effect on together with the dark energy. So the dark matter does not exist independently of the baryons.
Erik, this is probably an obvious question. So if you look at that equation, is this true only in a background that's de Sitter space?
This is the way I derived it, and I have therefore not looked at cosmological evolution, for instance. If you write on FRW universe, you may ask, what is this parameter? Is it determined by the Hubble parameter? Is it determined by the cosmological constant? And how does it depend on time? These are questions I have not looked at, because I really started from the system I've looked at. I've taken the system, Sitter space, and I took ordinary matter as a small change in that state. And then I calculated this. So I have thought about showing you a plot how this might depend on time, but since I don't know how to answer the question about what is the role of this parameter, is it really the Hubble parameter or maybe some apparent horizon distance. I mean, there's many parameters that start coming in when you take the dynamical cosmos. And they could all play the role of this one.
Okay, because usually physicists think of the Hubble parameter as a nuisance, as a nuisance parameter. But here, you think it might be some fundamental?
Yes, so I indeed claim that what is essential for the whole approach that I'm taking is that there are two scales in the problem, a Planck scale and a UV scale and an IR scale. It's set by the amount of entropy that I put in, and that large number basically determines the dynamics. So there is not just a UV physics description, you need also the size of the system, and that for me plays a very important role. And so for me then, those two parameters are almost equally fundamental.
Would you predict a dispersive propagation for gravitational waves?
No, actually in a certain way, I try to make that point there. There's a short time scale behavior that is very well described by GR.
What about long period gravitation?
Very good question. There as it goes to the question of also the dynamics, I'm not going to make predictions unless I to the point where when I really understand my theory well enough, because otherwise I start making claims that I have to change the next day. So I don't have, actually this is also why I have this on the last slide. I basically say that for the moment I believe that lots of the things happen very similar to what's happened in the standard cosmological, It's this last thing. Where are the differences appearing? Here I really want to make sure that I understand it well enough before I make my prediction.
So you may just have answered my question with your answer to the last question, but in that sense, if you're looking for something to discriminate between GR and this, I don't know what you would say. So if you were to discover dark matter, would you say that?
Yeah, so
and given, so sorry, the second part is if you, even at some scale that you might not now be able to measure, is there something already there would be, if you imagine like a parakeet or some difference in the scale?
So, so our solar system, I think, is in a range where we have a high acceleration, where lots of these ideas, I mean, what I've just talked about is not applicable. Even made approximations, I'm not in that range. So someone that uses my equations and tests it in the solar system is not applying the equations in the regime where I derive with them. So I don't expect anything, and also Earth-based experiments I don't see. I really think the differences are in the cosmological setting. And so I hope that there will be some phenomena there that it's very different from GR that I can point to. But as I said, I want to be more sure about what this theory really says. And then more work needs to be done, also about understanding it microscopically, but also the dynamical questions.
Would you say dark matter if it's found?
Oh yeah. So if dark matter is found and we can be sure that it is present in the right abundances to explain these phenomena, this theory is wrong. That's good.
Recorded that. We have time for a couple more questions.
So is there any vague idea of what this high entropy degrees of freedom would be in string theory?
What it would be?
The degrees of freedom would be within string theory.
I call them long
Yes.
strings, but
No, right, but in that regime, I mean, do you have some ideas holographically or also in
so
the
string
vague?
theory is able to describe the entropy of black holes of arbitrary size in a certain way. I mean, we now understand it mostly in supersymmetric situations, but the general ideas are kind of always the same. And there are degrees of freedom that have indeed sort of what I would call the property of being very long strings. And we have microscopically some picture of how to describe them.
So syntax would be in the wrong, I mean, zero coupling, but you don't really know.
Yeah, there are of course developers and things like this, but I mean, I'm not claiming that this is going to be a very simple, solvable, weakly coupled description, but that may not be what the world is about. I mean, but I think qualitatively we have an understanding of what kind of degrees of freedom are responsible for entropy of black holes. Actually, this afternoon I had a discussion with Emil about exactly this. And it seems to be a universal way that it always appears in string theory, namely that there are excitations that have started getting lower and lower and lower excitation energies, and they can have enormous entropy by just exciting many different long-range ones. And those, by the way, are very difficult to interact with when you're just a local observer, because you basically decouple from them.
You mentioned elastic waves is real and what exactly?
Yeah, good question. I mean, so one thing that I did, I worked in a regime where I didn't even think about the full relativistic equations and so on, so there should certainly be more work done. But I do think that, say, in early universe physics, there must be ways in which they are excited, have been excited, and then maybe. But the other question already answered here is that the dynamics that I'm describing here is at a very different time scale than the one we are accessing with our any local experiments. It's not like we have a probe to directly generate them, but there may be ways that they affect observations that we are arguing. I mean, I'm certainly interested, actually, these waves are the ones that I want to use to explain CMB or acoustic oscillations in some other ways, because this may be the alternative way of doing this than the dark matter ones, because you might have a similar phenomenology.
Let's thank, we want to leave time for the non-PhDs, actually. Are you willing to, we have a section for the non-PhDs to come down and ask you questions?
That's fine.
Okay, good. So let's thank Erik once again.